Hello, everyone. Welcome to CS6515, Introduction to Graduate Algorithms. Hello, everyone. Welcome to... Let us start with the questions about homework 1. So to address multiple questions together, I would briefly explain what problem 1 and problem 2, the graded problems from the homework, are asking. The first problem is asking for a substring common between two given strings to be computed. But its characters should be consecutive in the first string, but not necessarily appearing consecutively in the second one. And the example presented in the problem statement should clarify this. And please note that the length of the first string is assumed to be n, and the length of the second one is assumed to be m. As an example, if we have x and y to be equal to these strings, the answer, the solution, would be BDBA, which appears as a substring of string x in consecutive positions, and appears as a subsequence of the second input. So it is a hint that the solution to this problem will be a dynamic programming solution. In the first part, you are asked to define your table entries in English language, and it is going to be the state of your dynamic programming, if you have heard about it. So here you will just define a subproblem that is going to be solved using dynamic programming method. And as in other dynamic programming solutions, the state and each entry of the table is solved using other subproblems that are usually smaller. So, and we will name it a recurrence relation. It will be explained in part B. And in the third part, you are asked to write a pseudocode that explains your solution. So some students asked about the rules of a pseudocode. Generally, pseudocode is something that a human is going to read and understand. And we represent our algorithms in pseudocodes to be more readable and more concrete. But a computer is not going to compile them. So you are free to use, for example, brackets to indicate an element in an array, or parentheses. Or you may use a for loop in notation of C++, or any other language that can be interpreted by human. And in the part D of the problem 1, you are asked to analyze the runtime of your algorithm. So there were more questions about problem 2. Let us see an example for problem 2 of how the input may be given. So the problem statement is asking to compute the minimum number of semesters that the student can finish the curriculum that satisfies prerequisite relations between courses. So it assumes that we are having n courses, and each course may have some other prerequisites that are courses that need to be taken before this course. So let's assume that our courses are represented by numbers from 1 to n. So in a sample input, we may be given 5, which shows we're going to have 5 courses. But we also need to be given the relations between courses, that which courses should be taken before which. So you can assume in each line of the input, a list of courses that are required to be taken before that course are given. So for example, for the first course, we are given nothing. So we will have an empty line. For the second course, we may have that it requires course 1. The third course may require that 1 and 2 need to be taken before that. Fourth course may require only 1. And the fifth course may require the third course. it may be good to look at this example in a visual sense, in which I will draw course 1, and I will have course 2 that requires it. Then I am told that course 3 requires both course 1 and 2. Course 4 requires only course 1. And course 5 requires course 3. So this example was just provided to get a sense of what the problem is. But you can think of the problem in general for the case in which we have n courses, and you can define a new parameter, for example, the total number of dependencies, and name it m, and provide a solution. As a hint, it will be most likely a dynamic programming solution, as it is the subject of the study in the first few weeks. And analyze the runtime of your solution based on n and m. So someone just asked that, can we have more than one dependency for a course? Yes. For example, in this example, we have course 3 requires both course 1 and 2 to be taken before that. So getting back to the questions asked on Piazza, the first question is about problem 2, which we just talked about. So the next question asks, is problem 2 for homework 1 associated with chain matrix? So we solved chain matrix multiplication using dynamic programming technique. But this problem is not aimed to be directed towards that problem. There may be some relations, but I would, if I just want to answer this question in one word, I would say no. So the next question asks about whether you have to use pure dynamic programming algorithm for homework 1 problem 2 to get full credit or not. So being able to use dynamic programming is actually a hint, but you are free to use any algorithm as long as you provide analysis, proof, citations, and you may even gain more credit if you provide better solution than the best dynamic programming solution. And it is pretty hard to define whether a problem is a dynamic programming solution or not. These are just ideas that humans express to reuse these ideas in solving different solutions. So one solution may be expressed in different languages, and one could be dynamic programming for it. For example, one of the students asked a good question, that is dynamic programming a part of divide and conquer or not? And she has felt that these algorithms are very similar. So this is a very good point, and both dynamic programming and divide and conquer, and even some other ideas that we will see through the course, have many ideas in common. And the thing here is that they both use smaller instances of the problem to use bigger instances. But in divide and conquer, we usually know where to cut the problem into pieces. For example, in merge sort, we divide the problem in two parts and solve each one individually. So that is a great example of divide and conquer. But in dynamic programming, we usually iterate over multiple cases that may be the breakpoint for getting smaller problems. That is why we study these two ideas separately, but they have similar intuitions. So another question about homework 1 problem 2 asks, is the input in an adjacency list format? So the way we expressed in this example was exactly an adjacency list, with the difference that for each vertex, we just assume that its prerequisites are expressed in a single line. One may assume that the number of those vertices is given and then they are enlisted. But you can assume that it is in adjacency list form. And time complexity should be expressed in the parameters that you assume define the size of the input given to your algorithm. For example, the way I expressed it here, I assume that there are n courses and there are m, which is the total number of prerequisite relations. So if I provide an algorithm, I would expect it to be analyzed based on n and m. For example, one may analyze a solution to be O of n times n. I'm not saying this is the optimal solution. I was saying the answer should be expressed based on parameters n and n. And the third part, it is asked that if topological sort be used to pre-process the input, is it needed to include the pseudocode for that? As long as it would be referenced ideally from the book, no, there will be no need. And you can assume that it takes a particular amount of time. And consider that in the analysis. So it was previously mentioned that the better runtime of a solution, it will gain more points. And the default thing to analyze for the solution is the runtime. So in a question, it was expressed that, is there a bonus for better memory complexity for problem 2? That was a good question, and in the optimal solution, memory complexity can be lower than time complexity, but because it is not asked in the solution, there is no grade for that. it is only required the runtime of the algorithm to be as small as possible. So similarly, for problem 1, you don't need to further optimize the memory complexity because it is not expressed in the problem statement. And one question was, is there a schedule for when our future homeworks are due? We approximately will have 8 homeworks, and that will give roughly 1 or 2 weeks per homework. But you can ask for more details in Piazza. And we have another question about guidelines for pseudocode. So as previously mentioned, you are free to use brackets, parentheses, and colon, semicolon, as long as you think that a intelligent person can, it does not need to be compiled by a computer. A human being just needs to understand the pseudocode. For example, in a programming language, the function max may only be able to take 2 inputs, but you can easily use 3 or more inputs to the function max, and it will explain, it can easily be interpreted by a human. So there were 2 questions about fast Fourier transform. We will get into detail for fast Fourier transform in next office hours, which will be the subject of homework and study. But as to mention, so briefly, the question asks why we divide, why we split the array A into A even and A odd. It means even indices and odd indices. And the reason is that because then we can have a similar subproblem of smaller size that can be solved recursively so that the divide and conquer method can be used, because it is going to split the problem in 2 halves and solve each one with the same method. Another question asks if the solution should be optimal. For example, if the optimal solution is n squared and someone provides n cubed solution, what will happen and how much penalty will there be for it? So there will be penalty, and if the optimal solution is n squared, if the dynamic programming optimal solution is n squared, the full credit is given only to n squared solutions. But as long as the solution is polynomial time and it is feasible, it will get some points, but the amount of points that will be lost depends on the problem and the difference between the optimal and the provided solution. So I'm reading some of the questions from live chat. So for question 2, n assumed to be the number of courses and m assumed to be the total number of prerequisite relations between courses. For example, in the sample input that we have on the board, n is 5, and m is also 5 by accident, because 2 requires 1, 3 requires 2, 3 requires 1, 5 requires 3, and 4 requires 1. For example, if we add one more requirement for course 2 and require that course 2 would need course 4 to be taken prior to, the input will change to look like this, and m will be 6. So in this scenario and formulation, you are required to represent the runtime of your solution based on n and m. For example, it might be n plus m, n times m, n squared times m, and you can analyze your solutions in O notation, in big O notation. So a good question was that how can we recur when the courses are not in the specific order? For example, in the sample input on board, course 2 requires course 4, which its number is larger, so you cannot assume that a course will require only courses with smaller number. But you can assume that there is no loop, because then the student would not know which course to take first. We will not have a course X that is required by course Y, and Y being required by course Z, and Z being required by course X. So you are guaranteed that the input, in a feasible input, this kind of thing will not happen. But you should find the good ordering to do the recurrence or something similar to this on yourself. So as a hint, I would say the most useful hint is the presentation I provided on board for the example. The way we present courses with circles and show the relations with arcs, and to think that in that presentation there should be no cycle. So again, M is the total number of course requirement relations between pairs of courses. That's right. In graph notation, N would be vertices and M would be the number of edges. Yeah. For example, one has asked 3 cannot be prerequisite of 1 so that no cycles form. That's right. We should not have cycles. And one other question is whether the graph should be reversed or not. It depends on the definition of arc, whether you would like to represent an arc from X to Y to that X requires Y or that Y requires X. So in either case, it works. You just need to define it. So let's see whether we have more questions from Piazza. So the questions were asked to be put on Piazza to be more ordered, and we can schedule time and see which questions are asked more. That will then, and this thing will help in future office hours. But you can also add comments in the live chat of the stream, and I will check them too. So one question asks whether DP can sort a DP solution can sort the input. Of course it can. You can reorder the input, and part of your solution be dynamic programming. It doesn't need to be only dynamic programming. So one question is about table definition and notation in dynamic programming solutions representations. And by a table, we aim to define a subproblem. For example, in the problem of largest common substring that we saw to be solved by dynamic programming, a P of I and J could be defined as the length of largest common substring using the first I characters of the first input and the first J characters of the second input. And it is just a name that we use because we usually store these numbers in arrays and tables of our programming language. For example, it can be implemented in a two-dimensional array in C++ language, where this notation would be used for it. And again, to mention that you are free to use both of these notations in your pseudocodes, because one can understand it. So if there is a specific dynamic programming problem that you would like to be gone through and we solve it. Even if it's repeated from the course, feel free to ask it in the live stream or any other questions. So 2 questions. The second asks whether 4 is a prerequisite of 2 or vice versa in this example on board. So we have that course 2 requires 1 and 4. This is the line corresponding to requirements for course 2. So, and we have defined our arcs to show dependency in this sense that 2 requires 1 and 4, so we draw from 1 and 4 towards 2. So it is saying that 2 requires 4. And the previous solution asked whether we need to edit a table in our algorithm or can we recurse or edit on the input. So assuming that you are storing input on an array, you can modify the input. You don't need to preserve it. You can modify any data given to you, or even assume you are modifying the input file and its lines that are given to you. But it is usually suggested and easier to define a new table and initialize some values in the dynamic programming table and then use the recursive relation to fill other values. The last problem asks about problem 2, the last question. And it is not defined in the problem statement whether prerequisite course is given or course prerequisite. So you may assume either of these, but express this in your solution so that it will be self-representative. And the previous one asks about in the LCS recursive relation, on how we can deduce the relation for LCS. So as we noted it, let's get into that quickly. So here I would define the LCS subproblem Lij to denote the length of the largest common substring for two prefixes of length I and length j of the two inputs of the problem. And we know from the course that the answer will be this relation, which I will explain why. So there are two cases for solving the subproblem of Li and J. We look at the characters index I and j from the input strings. If they are not equal, we can be sure that in the optimal solution, which is the largest common substring, both I and j, both xi and yj cannot be present because they are not equal to each other, which is the second case. At most, xi or xj will be used. So at least we will lose one of these two characters. If we don't use xi in the optimal solution, the answer will be at most Li minus 1 and j, because we will have indices 1 to I minus 1 from x and indices 1 to j from y. And in the other case, the optimal solution will be at most L of I and j minus 1, which is the case when we will not using yj. And the first case was not using xi. At least one of these two cases would happen because xi is not equal to yj. And the common substring cannot have both of them at its end. So this was the easy case. The previous case was if they were equal. So here we just have been going the safe way of considering all three cases, that the two cases are not, the first two cases are not using the xi. Second one is not using yj. And the third case is because they are equal, we can use both of them. And if we use both of them, then they will be matched to each other, and we will get a +1 for this last character that we have used xi and yj. And we are remained with two smaller substrings to solve the problem for. So there are multiple questions asked about shortest path and problem 6.4 from DPV book. And I don't know whether we have time for all of them, but we will try to get to as many as possible. But I'm making sure that all questions relevant to the homework for which the deadline is near are answered, so we can discuss the remaining problems in the next office hour. So about problem 2, it was asked about the arrows. So let me check what we had. So it is asked, why is there an arrow from both 1 to 2 and 4 to 2 if both 1 and 4 are prerequisites of two? So I defined my arrow from, if I drew an arrow from x to y, I defined it to mean that y requires x, and x is a prerequisite of y. But you can define it in either case. You can define the meaning of your arrow to be the other way. But as long as you be consistent, there will be no problem. So in our example that we drew, 2 required 1 and 4. So we drew arrows from 1 and 4 towards 2. 4 required 1. So we drew from 1 to 4. And 3 required both 2 and 1. So we drew from 2 and 1 towards 3. So thanks for these questions. I think the questions we didn't have time to mention were the shortest path and problem 6.4. I think as the shortest path is more relevant to the homework, let's discuss it first, as it is part of the one of the main ideas of dynamic programming. Or please update the live chat if there is any other question relevant to the homework, which is due in a couple of days or less. So I want to go very quickly over the shortest path problem. And we assume that we have a graph that is given by a set of vertices and a set of edges. We are given a vertex S, and we want to compute the distance of all other vertices from S. So if S has some neighbors, their distance from S would be 1. But their names may be different. The distance of S from itself will be 0. And this is the parameter that we use to provide our dynamic programming solution. So T of every vertex, this is the subproblem that we define and will solve recursively. The T of every vertex is the shortest distance of a path from S to that vertex. And we do the initialization by setting T of S to 0. And T of all other vertices, for example, it's just a matter of name. So for all other vertices, let's set their T to infinity. Or a flag that shows that we still haven't computed the T for them. And while there exists a vertex for which T is not computed, or we can represent it in another way. Say, while we have not computed the distance to all vertices and show the vertices for which we are finished by a set, I would name it X here. While X has not become the whole vertex set, let V be the vertex not in X, and minimizing T. So in the first step, we will be S. And what we are going to do is we update the value of T for its neighbors. Mark V and update all its neighbors. So in the first step, S updates in the first iteration of the while loop. S updates the t value for its neighbors, and the value of t for S is finalized. We add it to the set X. In the next step, one of its neighbors will be picked because they minimize t, and they will update their neighbors and will be marked into the set capital X, and so on. So this is almost the amount of time we got. Please ask if there are any questions relevant to homework 1. And we will still be connected through Piazza. So that last question was a good one, that asking whether this solution for shortest path would be counted as dynamic programming. Yes, because we are defining a sub-problem, T, for every vertex, and solving T based on other values of T. A neat difference here that one would note is that here we are using previously computed values to compute the non-computed ones. We are updating forward. But many times in a dynamic programming, we use backward updates. And for bigger ones, we use the smaller ones. So if you use a standard kind of sort, you can just name it. If it's famous, just name it and consider its runtime in the analysis of your solution. Ideally, you can provide a reference to a section of the book that explains that algorithm to make it. So thank you, everybody, for coming. Also, if you came late, you can later watch this video on YouTube. And the last question. Yeah, it is generally okay if you define your solution in words, but many times things like pseudocode and mathematical notations make it easier for another person to read your solution. So I always suggest using them. Thank you very much. Have a good night or day, and good luck.